In this tutorial, I am going to show you how you can quantify RNA Seq reads using the tool FeatureCounts. So what we are going to do is to perform these three activities. We are first going to get our data. So we will download the sequence reads, and we're also going to download our reference sequence. And after that, we will map the reads to the reference sequence, and we will quantify the mapped reads. Please take note that these three activities are part of a bigger workflow that is used for RNA Seq data analysis. And so this means that there is more to what I've indicated here when it comes to RNA Seq data analysis. But the focus of this tutorial is to show you how to quantify the reads, and that is why I have limited the activities to these three. Okay, so that's what you need to know. And I've covered one such tutorial where I showed how to perform RNA Seq data analysis. And there are different tools available. So that means the workflows change slightly when it comes to RNA Seq data analysis. So you can start by watching that video, which I use HiSAT and other tools to perform RNA Seq data analysis. And I'll be making more tutorials on that. So make sure to come back and watch more RNA Seq data analysis in the future. The link to that video I made mention of about the RNA Seq data analysis is available in the description box. So make sure to check that video out. Now, if you want to follow this tutorial, you need to make sure your PC satisfies these requirements. You should have a PC with a RAM greater than 8 GB. And you should also have the number of cores of your PC not less than 8. For the software, you should have a Linux or MacOS operating system, and you should have star installed. We'll use star to map the reads to the reference sequence. You should also have FeatureCount installed. FeatureCount will be used to assign the reads to the genes or quantify the genes. And we are going to use multi-QC to aggregate the results that FeatureCount will generate. Instructions for installing these tools can be found in the description box. Okay, I've made tutorials, I've made videos that show how to install these tools. So check the description box for the links and then use them. Alternatively, you can use Anaconda to install these tools. So if you have Anaconda installed, you can use that to also install the tool. That's fine. So I'll show you how to use Anaconda to install these tools, by the way. So that's what we are going to do. So just check the description box. You'll find all the necessary information that is required in order for you to follow and reproduce this tutorial. So let's get started. This video is based on this Galaxy tutorial. I will leave the link to this page in the description box. So in this tutorial, the authors showed how to perform reference-based RNA Seq data analysis. Okay, so that's what this tutorial is about. But I am going to cover mapping and then the counting of the number of reads. For the mapping, I will skip the inspection of the mapping results. I've already covered that in a separate tutorial. So I suggest you watch that tutorial. In that tutorial, I showed how to perform quality control, how to map the reads, and how to also inspect the reads or visualize the reads using IGV. So I think that will also be a good start for you. So that's it. So for this tutorial, we are going to get the data, perform the mapping, and move straight to counting of the number of reads. So that's what we are going to do. So let's get started. So first of all, let's look at the data. We are going to use these fastqc files. Let's check them. Yeah, these are smaller ones. We are going to use these ones. And then we are also going to use the reference sequence. Now, for this data, we are dealing with this organism, Drosophila melanogaster. So the sequence reads are for this organism. So take note of that. So we will need to also get a reference sequence. So we will need a fastqc file and then the DTF file. I think the DTF file, we can find the link somewhere here. I found it here. Let's scroll down. The link is here. So we have it here. And then for the fastqc file, we will check it on the UCSC website. So this is the UCSC page where we can download the fastqc file. I'll leave the link to this page, and I'll also leave the link to this page in the description box. So that's what we are going to do. Now, because we have a couple of files, what we are going to do is to get all the links into a script. We will write a script that will download all the necessary files for us. So what we need to do is to get the download links, and then we will use that to download the necessary files. So let's go back to a terminal and then prepare our environment. Okay, we are on the terminal now. So what we will do first is to create a working directory. So we will say make the RNA Seq, and then we are going to cd into it. And so this means that files that we will generate will all be stored or saved in this directory. And it's important we do this because we would like to separate all the files that we are going to generate from files that are already on our PC. Okay, so now we have created it, we have seeded into it. So what we are going to do next is to download the necessary files. So first of all, let's go back. We need to organize our links. So let's go back to the various web pages or the various places where we can get the download links. Okay, so we will start with the Galaxy page where we have the files we will need. We will use these files. We have 2 samples here. Then we also have our GTF, which is the reference sequence here. Then we also have our fastqc file, which is here, this one here. So we are going to get all these files. So we need to get the links. So first of all, let's go back to the terminal. And then on the terminal, we are going to create a script. And in that script, we will place all the links and then execute that script. So we will do a batch download here. So I'll say nano download data.sh. I'm using nano, but you can also use VI or any text editor for that matter. So take note of that. So I'll open it and then I'll go and then bring all my links. So I'll start with the Galaxy platform. I'll check the files I have. I'll use these files. So I'll copy all the links and then I'll paste them here. So I have my scripts opened. I'm going to edit. So I'll paste the links there. These are the links. I'm going to use wget to download. So I'll just place wget here just to get them there. I have them like this. So let's continue. So we have wget, but there is something else I would like to do, and that is to modify these names here. So I'm going to download them, all right, but I'll also rename them so that I have shorter names. So what I'm going to do is to keep only these ones, the ID here and then the one, which is used to distinguish between the forward and the reverse. We are dealing with paired and reads. So this one, for example, I will say -o, and then I'll put that name there, and I'll say .pascal sanga on somewhere. Let me do this. Let me decrease the text size a bit. Okay, now it's okay now. So I'll do same for this. So -o. I'll paste this here. I'll say .pascal sanga just to keep them. I'll do same for this. Then I'll do same for this. Please note that this O is uppercase. Okay, so I have them there. You should also know that what I've done here, there is a better way of automating the download process, but because I'm assuming that some of the viewers may be beginners, that is why I'm trying to make it in this way so that you can understand whatever I'm doing. But there are ways to automate this process, okay, without you having to specify wget every time. But these are things that will be good for advanced people, but that's something that we'll cover in another tutorial. But if you're also interested in automating some Linux activities, you can always reach out to me. I will leave my contact in the description box. Now let's get the reference sequence. We will need the fastqc file and then the DTF. So let's go and get the download links. Okay, so let's first get the DTF, which is here. Should be somewhere here. Yeah, this one. We will get this link here. Or actually, let's do it this way. We don't need to use the DTF here. We can still use the one here, the one in this particular web page. Ideally, it's advisable to download the fastqc and the DTF from the same database. So I'll download everything here. I think that should be better. So let's download the ones here. So we get the fastqc and then the DTF. So the DTF can be found in the gens directory. So first of all, let's get this link. We'll right click and then copy the link. And then we will paste it here. So I'll say wget and then I'll paste the link there. Then let's get a DTF. So when we are here, just search for gens, this one here, click it, and then you see the DTF, which is here, dm6.ensgen.dtf.gz. So let's get this one, right click, then copy the link. And then you can paste it here. So I'll say wget, and then I'll paste the link here. So this is the link for the DTF file. So that's it. So let's save the changes. And then let's execute the script. Now with the execution, you can use bash like this and then call the script and execute it. Or you can also use this approach where you say slash. You can do it this way. I prefer to do it this way. So if I'm going to do it this way, then I need to modify the script again. I'll use this opportunity to show you a couple of things when it comes to writing scripts. So I'll go back again. I'll say nano. I'll edit the script here. Then the first line here, I'll say /bin/bash. So this tells Linux that whenever we execute the scripts, bash should be used to run the commands here. That's basically what this means, the shebang line. So I'll exit the script again. I've made the changes. Now I'm going to add execution rights. So I'll say chmod +x. I'll say download data.sh. So I'll have it done this way. So now let's do an ls. We should find download data.sh here. Okay, so now we can download the data. So I'll use // now call it this way, but you can also use bash and then also call it. So whichever one is appropriate, use that one, but I'll do this // and I'll download the data. So let's download the data now. Okay, so the files are currently being downloaded. Okay, all the files have been downloaded. So let's check them out. Let's do an ls and then check the files. So we have our fastqc files here. We also have the reference sequence, the DTF and then the fastqc. These two files, you can see that the extensions are .gz. That means that they have been compressed. So we will process them. Now we are going to place the fastqc files in another directory. So let's create a directory. We will say make the data. And then we are going to say make the data slash fastq. I'm doing this so that I can group my files. Okay, it also makes my work more organized, and it's easy to locate files if you have naming conventions, and if you also have folders that you can put them in. So I'll move all the fastq files into this directory. So I'll say mv, and I'll say gsm. Let me use gsm, and I'll say star. So all files that begin with gsm will be moved, and we can see that we have 4 files. 1, 2, 3, 4. These are the fastq files. So I'll move them to data slash fastq. So now if I do an ls into data slash fastq, I should see them there. Okay, so that's what we have done now. So we have our fastq files ready. Now let's work on the reference sequence. Let's do an ls again. Of course, we will see this directory, but we are going to look at our reference sequence here. We have the DTF, we also have the fasta file. These are gzip, they are compressed, so we need to decompress them or uncompress. So we will first start with the DTF here. So we say unzip em6.ens, and then we complete the name. So let's uncompress this. So we are using the unzip utility. So now let's do an ls, and you will see that it has been uncompressed, and that is why it no longer has the .gz as an extension. Let's work on the fasta file. We say unzip em6.fa.gz. So let's run this command. That has also been done. So we can do an ls and then see that's there. Let's do one more thing. I normally prefer to have a naming convention for my files. So what I'm going to do next is to rename this DTF file here. I am going to remove this name here, the ENS gen. I will remove that so that we can have the same base name for the reference sequences, and then these names will be followed by their respective extensions. So I will do that as well. So I'll rename this one here. So I'll say mv dm6.ensgen.dtf, and I'll say dm6.gtf. So let's do an ls, and you will see that's there. So now we have these 2 files, which are also good. So we are going to move these files also into this directory. So we will create a directory called ref. So I will say make the data slash ref, and then I'll move these files there. So I'll say mv dm6 star. I'll say data slash ref. So they have been moved there. So that is good. Now let's check those files also out. So let's do an ls, and let's say ls data. You will see the ref directory there. So now we are going to say ls data. Let's do it again. You will say ls data slash ref, and then we will have our files there. So now we have our files ready. So it's time to proceed with the next activity. So let's continue. I am now going to show you how to install the tools using Anaconda. So first of all, make sure you have installed Anaconda. Instructions for installing Anaconda can be found in the description box. So after installing Anaconda, the next thing you have to do is to add Conda channels. We will add 2 channels. So I'll start with the first one, which is Bioconda. So I'll say Conda config add channels, and I'll say Bioconda. I'll add a second one. So I'll say Conda config add channels, and I'll say Conda forge. You can also confirm if the channels have been added. So you can say Conda config show channels. This will list the channels. So we have Conda forge, we have Bioconda. The default channel comes packaged with Conda, so we will leave it as it is. We are now going to install the tools. So we will first create an environment and install the tools in that environment. So we will say panda create-n, and I will say RNA Seq. So the name of the environment is RNA Seq. We are now going to specify the tools that we want to install. So we will start with star, and I also say SubRead. FeatureCounts is part of the SubRead package, so we are using SubRead. We are also going to install multiqc. So now we can run this command. We will now type Y to confirm, and then Conda will download all the necessary packages and install them for us. So let's wait for Conda to complete its work. Okay, the packages have been installed. So if you want to use the tools, you need to activate the environment. So you have to use this one here. And if you are done, you can deactivate using this one. So let's test the tools first. So if you want to test the tools, you need to first activate the environment. So you can say conda activate RNA Seq. And this will activate the environment. So after that, you can test. So let's just start. We will start with star like this, and then we can run it. We can also check where star is located, which is here. That's fine. So once you run it and you have this, that means that the tool is working. Okay, so we've tested with one. You can also do for FeatureCounts like this and then run it. So that's also done. So that is how we install the tool. So once you are done with the installation, then you can proceed with the other activities. So let's continue. What we are going to do next is to map the RNA sequence to the reference sequence. We are going to use star to do this. If you are going to use star to map RNA sequence to a reference sequence, you need to first generate a genome index. So let's go to the star documentation page and look at the instructions we can use to generate our genome index. We are on the page now. I'll leave the link to this page in the description box. So when you are here, scroll down to this section, generating genome indexes. So if you want to generate a genome index, you need to first call star, and then you indicate the options here. Some of the options are mandatory, some of them are optional. So let's take a look at the options here. We have run thread n, which is used to specify the number of threads. We have run mode, then you indicate genome generate. This is compulsory, it's mandatory, you have to specify that. We also have genome dar, which is used to specify a directory, and this directory is where star will save or store the output files. We also have genome fasta files, and this is used to specify the fasta file that you will use. If you have more than one fasta file, you have to specify all of them. So file 1 space file 2 space file 3 in that order. We also have sjdb gtf file, which is used to specify the gtf file. This one is not compulsory, but it's recommended. If you have the GTF file, it's recommended to specify that. We also have sjdb overhang. Here, I will skip this one. I will not include this. I will use the default value. So what we are going to do next is to go back to the terminal and then write a script. The script will contain the star command that we will use to generate the genome index. So let's go to the terminal. We are in the terminal now. What we are going to do is to create a directory called index. So this directory is where star will save or store the output files. So we will say make the index. Let's do an ls to check the directory. So we have that here. Now we are going to create a script which we'll use to generate the genome index. So I'll use nano, but you can use any text editor of your choice. So I'll say nano, and I'll say generate index.sh. I'll execute this command, and then I'll start with my shebang line. Then I'll say star. I'll indicate the number of threads. which is 8. I'll use the slash and then move to the next line. I'll indicate my run mode, which is genome generates. I'll indicate my genome DAR, which is this one here. And I'll say index. I'll indicate my fastqc file. That is what data/ref/dm6.fa. I'll indicate my GTF file, which is data/ref/dm6.gtf. I'll specify another option here, which is genome SA index n basis. I will say 12. So we have everything ready. Okay, so we are going to exit this editor, and we're also going to save the changes. Okay, so now let's do an ls, and we will find the file there, this script here. We are now going to add execution rights. So we will say chmod +x, then we specify the file name. Now we are going to execute the scripts. Then this will generate the index file. So let's do that. I'll say // then I'll call the file. So now star has started its work. It's now going to generate the index files. Okay, star has done its work. So let's check the output files. Let's do an ls just to check some stuffs here. So we will now ls into the index directory. So I'll say ls index, and I'll see my output files here. So that's what we have. So now we are ready to map the RNA sequence to the reference sequence. We are now going to map the RNA sequence to the reference sequence. So let's take a look at the files again. So I'll say ls data/fastq. So I have the files here. I have 2 samples. We are dealing with paired and read. So this pair belongs to one sample. This pair belongs to another sample. Let's create a directory called map. So I'll say make the map. I'll ls to check that directory. This is the directory, and this is the directory where star will save or store the output files. Now let's go to the star documentation page and look at the instructions we can use to map the reads to the reference sequence. So let's go. So if you're on the page, just scroll down. This is page 5. So click more pages, then go to page 7. So this is 6. Let's go to 7. Then you will see this section here, running mapping jobs. So if you want to map reads to a reference sequence, then you need to call star, and you also need to indicate some options here. We have some of the options here. So we will specify all these options, these 3 options, and I'm going to add 2 more options. I have run thread n to specify a number of threads, genome DAR to specify the directory which has the index files, and we also have read files in to specify our FastQC files. If you are dealing with single end reads, it's read 1. If you have paired end reads, then we have read 1 and then read 2. So let's go back to the terminal and then perform the mapping. So we will create a script, and then in that script we will place in the star command that we will use for the mapping. Okay, we are on the terminal now. So I'll create a script. You should also take note that we are dealing with more than one sample. So we need to find a way to automate the mapping process. We need to find a way to make the script generic so that we can always factor in the different samples that we have. So I'll open the script. I'll say nano map underscore reads.sh. I'll start with my shebang line. Then I'll move to the next line. So here I'm going to define, or I'm going to give variables. So these variables will assign the file names to this variable. So we'll use read1 and then read2. Let's take a look at the files again, the fastqc files. So I have data/fastqc. This pair belongs to one sample, this pair belongs to another sample. So for each sample, we have read1, read2. If you're dealing with pair and reads, then there's going to be a character or groups of characters that will differentiate, or that will be used to differentiate between the forward and the reverse reads. So in this case, we have 1 and 2. So 1 indicates forward, 2 indicates reverse. So we have that there. So what we are going to do is to create variables for both read1 and read2, and then we will use that to process our data. So I'll start with read1. So read1, and I'll say equals. So I'll come back and then I'll pick the first sample, which is this one. So I'll pick the sample name, the base name here. I'll copy it and I'll send it here. So I'll say data/fastqc/ and I'll place in the ID, the name. And I'll say _1.fastqc Sanga. This is read1. Read2 becomes data/fastqc. Then I indicate the same ID or name, and then I _2.fastqc Sanga. So what we have here, we can always edit this and then place in our files and then still execute the scripts, and then we can get our job done. So let's specify the options we use for star. So I'll say star, and I'll say --run. So it's this way, star --run thread n. I'll say 8. I'll bring my slash and then I'll move to the next line. So the next line, I'll say --genome dar. Then I'll say index. This is the directory. Say slash again. I'll move to the next line. So the next line, I'll define my files. So I have --read files in. Then I'll say $read1 and then $read2. So look at what I have. This is $read1, this is $read2, because we have created the variables here. This is read1, read2. So the $read1 means that we need to use the actual values that were assigned to this variable. So here, it makes it possible for us to reuse the scripts without having to write all the commands again. All that we have to do is to specify the file that we want. Okay, so this is the file name. So we have 2 samples, this and this. So now I'm starting with this. So if I finish with that one, I will now come and then change the ID. I will use this one. So I can come back, change this ID to what I want, and then execute the scripts. So that's what we are going to do. So there's one way to automate commands, and there are other ways to do it. If you have lots of samples, you can use for loops as well. And you can also combine the for loops with some Linux commands to get all the files and then process them. So if you are interested to learn about how to automate scripts or how to run mapping activities when you have multiple samples, we have lots of samples, you can always reach out to me and we can have a session together. So just make sure to contact, because ideally, if you are doing RNA Seq data analysis, you may have lots of samples. Maybe you may have 10, 12, maybe 20, etc. So you need to find a way to automate the process. This approach here, I wouldn't recommend it if you have lots of samples, but because we have 2 samples, that is why I'm using this approach. So take note of that. I'll also make the scripts that I'm using for this exercise available. So if you want to start practicing, and this tutorial. If you want to reproduce this tutorial, you can check the description box. The link to the scripts will be given there. So let's proceed. So I have my read files also specified. Then I'll also specify this dash dash out some type. I'll say bam. I'll say sorted by coordinates. So here what I'm saying is that I want the output file to be of the BAM formats. I want a BAM file basically. That's what I'm saying. We have some files, we have BAM files. So I want the BAM file. So that is why I have the BAM here. And I also want it sorted by coordinates. So that's why I have this also here. So I will now do this. I'll come here. I'll say dash dash out file name fix. This is what I'll use to specify my output file names. So I'll say mapped slash, and I'll say GSM, this ID here. This is what I want. Okay, so now I have the script complete. So I will exit and save the changes. I will now use this to add execution rights. So chmod plus x map, that's called reach.sh. So I will do that. So now I can execute the script. So I'll say dot slash map reach.sh. So this will perform the mapping. We specify this sample here. So that means we are going to map this reach to the reference sequence. So let's run this command. Okay, star has finished mapping the first sample. So let's proceed. So I'll say ls, then now ls into this directory, the map directory. So I'll say ls mapped. Now see the files there. So I have the output files here. So this is the BAM file, and we also have some log files here. This, and then we also have this one here. I've already explained these output files in another video, so you can check that video out. The link to that video is in the description box. You can also watch that video by the link right up here. So for this tutorial, I'm only going to focus on the BAM file here, and then we will just display this one also here. But let's map the other sample as well. So let's edit the script again. And this time we are going to use this ID here. So let's first copy it. Then I'll say nano map underscore reads. And this time I will change this sample here, this ID here. That's what I'm going to do. The same goes for this one. So now I have the second sample. So you notice that I only modified the sample IDs here. All other commands are the same, because here this one represents what we have here. So whatever you put here is what will be used here. So let's map this other one too. And let's check this one too. We need to specify this and give the same sample name. So let's do this. So now we will do the mapping, and we also have the output files for this sample. So let's save the changes. So let's map again by calling the scripts. Okay, so star will map the second sample also. Okay, star has completed the mapping activity for this other sample. So let's check the map directory. Let's do an ls, see what we have. So we have all of them here. Okay, so we have them nicely done. So we can always look at the output files, and we can always differentiate them using the sample IDs. So we can proceed. So for the star outputs, this is the BAM file, There's also a log file for the mapping statistics, which is this one here. So let's just take a look at the mapping statistics for these samples. Let's check. Let's try what's this one here, So I will say it's a text file. So I'll use a Linux command to display. So I'll say cat mapped. Then I will specify that one, which is here. So I'll open this one. This is for the 177, the sample which has the last three numbers as 177. So I'll open this and I can check the mapping statistics here. So I'll focus on the uniquely mapped reads, which is this one here. It's what in terms of percentage, it is 82.20%. Ideally, we should have most of the reads, majority of the reads mapping to the reference sequence. We should have a high percentage. That is what we see here. So things are looking good. Let's look at the other sample. So I'll indicate that also here. And let's take a look at that. So that one too, we have the number here, percentage is 75.58%, which is also high. Okay, it's also high, so it's good. So we have high percentage. So we have high percentages for both samples. So that means that we are good to go. Now with the log file, with the mapping statistics, you can also aggregate them, then visualize all of them. Okay, so there's a tool called MultiQC. You can use that to aggregate this mapping statistics, then check all of them out. So, and also that can help you to easily compare them. Okay, because if you are dealing with lots of samples, it becomes very cumbersome trying to open each of these files and then reading them. So MultiQC can be used to make your work easier because it will aggregate all these reports together into a single file and also generates some plots that you can use for the analysis. So I will encourage you to use MultiQC for your QC. So that's about it. So let's proceed. So let's take a look at the map directory again. And this time, what we are going to do is that we will use the BAM files. That's what we are going to use for the next activity. So let's continue. We are now going to count the number of reads that were assigned to each gene. In other words, we are going to perform gene quantification. We are going to use FeatureCount to do this. For the FeatureCount command, we are going to use the options that were stated in the gallery tutorial here. So we have the FeatureCount section and we have strand information. We have the annotation file, which is used to specify the GTF. We also have options for paired and reads. We are going to use this option. We also have the minimum mapping quality per read, which is 10. We will use that. We're also going to use these options here. So that's what we are going to do. And after that, we are also going to aggregate the results using MultiQC. So let's go back to the terminal and then run the FeatureCount command. So we will call FeatureCount and then we will supply the BAM files to it, this one and then this one. Before we do that, let's first create a directory. So we will say make the counts. So this directory is where we will store the outputs. So now we have a directory created. So we will say FeatureCount. And then we will say -t. And then we will say 8. That means number of threads. We are going to say -s. That means unstranded. That will be 0. And then we say -p. So the -p indicates that we want to count fragments instead of reads. And then we are going to say -t. -t indicates that the feature type filter is exon. We are interested in exons. That's what it basically means. So you will specify exon here. Okay, so that is also done. We are also going to say -gene and say gene ID. So this means that we are going to use the identifier gen ID. Now we are going to specify another flag here, which is -q. So -q here is used to specify the minimum mapping quality. So here we are going to use 10. We are going to use 10. And we're also going to say -a to specify the GTF file. So the GTF file can be located here. data/ref/dm6.gtf. Then we are also going to say -o, and we will say counts/, and now we are going to specify one of the BAM files. We are going to count them, okay, file by file. So we are starting with this one. So we are going to use this as the output file name because we are going to use this BAM file. So we will say count/, and then we will supply it with the name, which is this one here. Okay, so that will be the output. We can also say .counts. Okay, so we have that here. And then we will specify a BAM file. So we are specifying this one. So we say mapped/, and then we specify the name of the BAM file. So let's run this. So FeatureCounts will do its work and then give us the results. So if you look in the count directory, let's just check again. If you look into the count directory, you'll see an output there. So this is for this sample here. Okay, so we can do ahead just to display that. This has the actual data to get the information here. Okay, so this is it. This is what we have. Now you can see a lot of information here, but don't worry, we are going to clean this up as well. Now let's also look at the gen summary here. We can clear and then just check that one. So we can say head counts, we supply it with the name, and then we give the summary here. So this will also give us the summary. Okay, so this tells us the number of assigned reads and all those stuff. So this is good for quality control and for statistical purposes. So we have that for one of the samples. Yeah. Let's ls into the map directory again. Now we are going to do it for this BAM file as well. So I'll copy this one here. And then I'll record the command. So I'll record the command. And this time we are going to change some stuffs here. Let's clear this once and then use this base command here. So the same options here. Then this time say -o count/, then we give this, and then the BAM file becomes, okay, so this one we have to complete it. So we give count/gsm, and then we add whatever name we want, and then we specify the BAM file, which is mapped/, and then we give the name of the BAM file, which is this one here. So let's run this command as well. Okay, so the counting has been done. So let's check the count directory. So we have ls, and we will see that also here. We can also display that as well, and then get the information there. Let's look at the summary also. We have the summary here as well. So we have those two files there. Now we have these two results, these two outputs. We can aggregate this information using MultiQC. So let's look at how we can do that. So we can say, let's first do an ls first. Let's ls again to the count directory. So now we have the counts. Okay, FeatureCounts has been able to quantify the agents for us. So to aggregate the results, we will use MultiQC. And to use MultiQC to aggregate the results, we say multi-QC, and then we say counts, and then I'll say star.summary. So this is what I'll do. So let's run this command. So multi-QC will get all the files for us, and then it will aggregate everything for us. So this is how we do it. So let's proceed. So now we are going to take a look at the outputs. We have multi-QC reports, we have multi-QC data. So we are going to take a look at the outputs. So let's go and then look at the outputs. So let's take a look at the report, which is here, this HTML file here. So you can open it with your browser. So when you open it, you will have the information there. Okay, so we have this plot here that we can use to interpret our results. So we have the plot here, we have number of fish, we have percentages, so you can choose the one that is appropriate for you. Let's focus on the number of reads. This is the multi-QC report. This is the general stats, by the way. This is the feature counts. So we are focusing on the feature counts results. So if you look at the plot, there is a color scheme here that you can use to interpret. So blue indicates the assigned reads, and then black is used to indicate unassigned. And we also have unassigned no features. So unassigned in terms of mapping quality is black. Unassigned in terms of no features is this color, which is like green. And then we also have this color, which is more like orange, which is for unassigned ambiguity. So you can use these colors to help you interpret the results. But I would like us to focus on the assigned. So if you take a look at both samples, okay, the number of assigned, okay, the number of assigned reads is higher, it's greater. If you take a look at it in terms of percentage, we have assigned for this one is 68.9%. If you take a look at this one, it's 73.1%. So these are a good, okay, scores. So well, because they are high, that means that everything is good. So we can proceed. We should always have majority of the reads assigning to genes. Okay, so once we have this done, that means things are okay. So this is how we use multi-QC to aggregate feature counts results. So that's it. Now let's go back to the terminal. Let's do an ls into the count directory again. You'll notice that we run feature counts on each of the files, but you can also run feature counts on all the files at once using the wildcard. So if let's say you have tens or hundreds of files or samples, then trying to use feature counts and then supplying each of these files will be problematic, or to be cumbersome. Let me put it that way, it might be cumbersome. And so feature count allows you to specify all the files at once, or files with particular names. I mean, using some Linux commands. So now we are going to run feature counts and supply all the BAM files, okay, so that feature counts will run through all of them at once. So let's do that. So to do that, we will issue the feature count command again, and then when we get to this output -o, I'll say counts, and then I'll say slash, and I'll say gen.counts. This will be the name of the output. And then when we go to the BAM file, we will say mapped/star.bam. So once we have this, we can run it. So let's run this command. So feature counts will perform the counting on all the files that have been specified. So now it's done. So let's take a look at the output. Let's do an ls into the counts. We are going to see gens.counts. Okay, so this is what we have. So again, you can do a head counts gens.counts to get this You can also do gens head count slash gens.count.summary to get that as well. Okay, that can be done. Now I want us to take a look at this one here, the gens.count. So let's go and open this file here using a spreadsheet software or a text editor. We will try both and then see what comes up. So I have the file here, this one here, which has both samples. So let's open it with a text editor. So this is what we have. So this is what we have. Okay. Now, if you open it with a text editor, you have this. You have lots of information here, which can be very confusing. So let's try to open it with a spreadsheet software. Okay, so I have opened it with a spreadsheet software. So if you open it, you'll get the information here. We have this one, which is giving a description. We also have this here. We have gen ID. We have chromosome. We have start, end, strand lengths. And we also have the lengths. And we also have this one here, the count for both samples. So we have the first sample, which is here. And we also have the second one, which is here. So there's the first sample. I repeat, there's the first sample. There's the second sample, which is here. Okay, so you can check them there. But then you will notice something. We have the information here, all right, but we can still clean this up, okay, so that we use it for some analysis. So if you take a look at this, this is the name for the sample. We have map/gsm 4611 align, etc. So it took the name that star assigned to the BAM file. So we have it this way. We also have it this way. So this name here, we can clean it and make it better, because ideally what we want is to use this one here, this ID here. That's what we want to use. And so you can write a bash script or Python script or R script to extract the information and properly format whatever is here. I already have a script that I use to process files like this, so I'll show you how that script is used. I'll first do an ls to display the file. Okay, so there's it. There's the script. Okay, so this script requires two inputs. It requires the read count file. In this case, it's gens.counts. Okay, it also requires a text file that contains the sample IDs that you want to use. So I have my text file here, and that is it. So I'll display it for you to see. So I'll say cat samples.txt. So I have the names here. So these names will be used to replace the ones in the original file here, because a new file will be generated. So this is how we execute the script. So we say // and then we supply the file name that is for the scripts. Okay, so we are basically calling the script, and then we have to supply it with the input. So we first have to supply it with the read count file, and that will be counts/gens.counts, and then we supply it with the text file which contains the name that we want to use, and that is samples.txt. Now let's execute this script. Okay, the formatting has been done. So if you do an ls into the counts directory, you are going to find a new file called gencounts.final.counts. What you need to know is that the script will always place the new file it generates into the directory which has the original file. Okay, so take note of that. And by the way, I'll leave the download link to this script in the description box, so you can use that to download the script and then use that on your own data. Now let's take a peek into this file. Okay, the one that we generated. It contains the read counts for the gens and then the samples. So I'll say head, and then I'll say counts/gencounts.final.count. So let's display the content. So we have that here. So we have gen ID. We also have the samples, this and then this. So we have the gens here. So the count for each gen in each sample will be displayed. Okay, so that's what we have here. So everything has been formatted nicely for us. Okay, we are now going to open the new file that we generated, this one here. We are going to open it using our spreadsheet software. So let's do that. Okay, so we are going to open the file. So let's first go into the counts directory, and then we are going to open it now. Okay, the file has been opened, so you can notice the difference. Just look at what is here. Let's just open it, and then let's look at what is here. Okay, so we have that here. Of course, you can also use some of the information here for other analysis, but then if you are going to perform gene expression analysis, then the information you need are the genes and then their respective read counts, and then the samples that the genes were identified in. Okay, so that's what you need to know. So, and if you have such a situation, you can always contact me, and then we can try and then also clean up the files for you. I'm going to make a tutorial on that, and I'm going to place it here or on my Patreon channel. I think it's may likely go to my Patreon channel, so you can always go there to check the script and then use that to clean up the data that you have. Or you can also just send me a message, and then I can also have a session with you and then clean up the files and then perform some other analysis for you. So this is how we do it. So after counting your reads, after performing the gene quantification, what you can do next is to perform gene expression analysis using tools like HR, Seq, Bourbon, etc. Okay, and so I will encourage you to watch the videos in this playlist. These videos show how to perform gene expression analysis. So make sure to watch that and then get more knowledge in RNA Seq analysis.